Okay, so welcome everybody to lecture A.8. In the last lecture, we introduced a new model of probabilistic proof, interactive oracle proofs, or IOPs. We saw how it extends simultaneously both the notion of an interactive proof and a PCP by essentially considering this interaction where the verifier receives from the prover multiple oracles, and it can query any one of them without sort of having to read them in full, like in an interactive proof. We also saw that IOPs do not bias extra languages, in that they are at least as powerful and no more powerful than NEX, simply because they have special, they can be unrolled into PCP, and they are at least a PCP. So it didn't help us there, but where we were able to apply them was to making savings in proof length. And specifically, we went back to the polynomial size PCP for quadratic equation satisfiability, and saw how with very few simple ideas, we were able to take the proof down from cubic to arbitrarily close to linear. However, we left open the question of whether can we even achieve linear size proofs. And that is the subject of today. We'll learn about how to construct linear size IOPs for circuit computations. Okay, so that's the goal for today. And specifically, we focus on the case of large enough fields. Over small fields, things can still be done, but it requires a bit more care, actually a lot more care. So instead of working with specifically arithmetic circuit satisfiability, we're going to work with a language that you have seen in a past worksheet, and it's something called R1CS, stands for rank 1 constraint satisfiability. There's no particular reason to work with this one other than arithmetic sort of circuits, other than the fact that it is notationally very convenient. Okay, it's just much easier, much more sort of crisp language to write down rather than you have to talk about like arbitrary gates inside some circuit. So, so the language works like this. An instance is given by a public input U and a collection of matrices ABC. All right. And the satisfiability condition says there exists a witness Z that satisfies this condition, A times Z, Hadamard product B times Z equals C times Z. So the way you should imagine this is that you have this matrix vector computation, and you're going to get two vectors, and you're going to take the entry-wise product, that's the Hadamard product, right, and compare it against this matrix vector computation. That another way to view it still is that you have a system of quadratic equations of a very special form. This form that is linear combination times linear combination equals linear combination, okay? So it's a type of quadratic equation satisfiability that has a very special uniform kind of structure, okay? That all the equations can be summarized like this, okay? So the rows of the three matrices correspond to the linear combinations that are going into this equation, right? And this restriction of quadratic equation satisfiability preserves NP completeness. This is something you can sort of, it's pretty easy to verify by yourself. So we'll take it as an NP complete problem and work with it, okay? And again, I believe you've had a worksheet where you constructed a linear PCP of linear size for this very problem. Okay, today we'll just construct a linear IOP for it. Okay, so the theorem we're going to prove is that for large enough finite field F, we also need it to be smooth. We'll kind of come back to that later. We can construct an IOP with perfect completeness, constant soundness, a logarithmic round complexity. And the important part is that we have the proof length is linear in a number of equations over the natural alphabet, which is the finite field, right? And the queries is going to be logarithmic, and so is the randomness. Okay, but the key point here is for arithmetic computations, we can achieve linear size IOPs. Okay, and this improves from in the previous lecture where we had something like n to the 1 plus epsilon with a trade-off over the queries. Here it's like linear and like a single logarithmic in the queries. All right. Now, notice that when you start hitting the regime of linear size anything, you cannot actually say linear size for all of NP. because just translating from one problem to another, you might hit superlinear overheads, okay? Now, in general, almost any reduction between an NP problem to another NP problem can be done in a quasi-linear time, okay? So if you're willing to absorb polylogs, you can claim things for all of NP, okay? But if you don't even want to allow for those extra logs, then you really are down to saying this language has a linear size IOP, and maybe there may or may not be linear time reductions from other languages to it, okay? So just, you know, like this is at a fine-grained enough where the notion of NP completeness cannot capture it so well, right? But it's fine, you know, this is a pretty useful language nonetheless. And you know, today, for simplicity, we're going to assume that the matrices are square. So even though we have technically two parameters, the number of variables, right, which is basically the number of columns, and the number of equations, which is the number of rows, we're going to consider things to be square. So m equals n. I may or may not still use m and n as separate parameters, but they will anyways be assumed to be equal. As a kind of remark, it turns out that this language of R1CS is not only very convenient from a, let's say, writing a protocol perspective and analysis, it's like really convenient to use. It is also used in practice in a sense that there are compilers that translate high-level programming languages into low-level so-called constraints represented through R1CS equations, as well as there are domain-specific languages where a programmer can directly express you know, some ideas they have in mind for some computation and kind of create, assemble these matrices. And the vast majority of deployed cryptographic proofs in the real world, actually, I would say maybe more than 80% of them are real-world cryptographic proofs where the interface ultimately to the, you know, kind of the user is like some constraint system of this sort. Okay, so it's unusual for this language to be like convenient both from a description, sort of pedagogical perspective, and also in practice. Okay, and in fact, some of the techniques that we see today, they are sort of not just giving you very nice asymptotics; they are, you know, rather practical protocols. Okay. Though we won't be seeing, you know, many of the optimizations that, you know, one has to like throw in to make things you know, truly practical. So there's a question by me. I'm thinking, you know, I'm fixing m equal to n just for convenience. Generally speaking, m is maybe close to n, but it is convenient in practice not to fix them to be close. Maybe m is like, I don't know, 4 times as large as n, or vice versa, and so you don't want to have to pad things for no reason. I don't know what happens. I don't want to try it right now to think about what happens in extremal settings where, I don't know, m is like logarithmic in n. That is not a good setting of parameters to think about. That's not what I'm thinking about right now. Right. Before we get started, any questions about the motivation or sort of what we're about to do? I'm not going to linger too much on this because you should have seen it in the worksheet. And hopefully it is clear that we're sort of aiming for a regime that we haven't seen before for PCPs. By the way, as another comment, the goal of linear size PCP, not IOP, remains perhaps one of the biggest open questions in the PCP world. Okay. We may or may not ever solve it, but it has been solved for IOPs. Okay, so that's one of those ways in which things have been simplified by having you know, multiple rounds of interaction. Questions before we get started? Okay, so then let's get started. So we kind of spent a little bit of time talking about kind of past encodings that we've used. It will be helpful to kind of do some recap here as well. So if you kind of look back, our recipe to construct PCP is primarily, you've seen 2 lectures about those, or the exponential size PCP and the polynomial size PCP with Tom yesterday and the day before. has been to basically construct a PCP that has two parts. One part, let's call it pi A, another one part called it pi sat, where pi A is allegedly the encoding of a candidate assignment. Okay, so it belongs to some and it belongs to some set of valid encodings. Okay, so in the case, I guess we'll come back to the case of in specific examples, and then if this first part is close to a valid encoding for something, then the second proof, the second part of the PCP is some string that facilitates checking that whatever message is encoded indeed is a satisfying assignment. Okay, so there is always this kind of two-part structure: encode the candidate assignment, and if the encoding is reasonably close to a valid encoding, then the second proof will let you check that it is indeed a satisfying assignment. That was kind of the paradigm we've been following. So, and what encodings did we use, right? So for the exponential size PCP, we used linear extensions, also known as the Hadamard code, right? We kind of encoded the Hadamard with satisfying assignment via Hadamard code word. In other words, the encoding was the function that maps f to the n to f, where the encoding of A was this whole big string, which of size, f to the n, right? As opposed to n. So you go from something of size n to something of size f to the n. For polynomial size PCPs, we used multivariate Ludegy extensions, also known as the Reed-Muller code, where the encoding was either like this, where there's multilinear extension. This is something that actually we used in the doubly efficient interactive proofs, or in the polynomial size PCP, where this was a kind of not a multilinear extension, but a sort of an extension of individual degree h, where h was something that ultimately was chosen to be of size log n, right? So it was, the number of variables was log n over log n, right? So the individual degree was log n, and the number of variables, again, log n over log n. So, and when we chose the encoding to be linear extensions, we had the linearity test, right? And when we chose things to be using Ludegy extensions over multiple variables, we had the Ludegy test to ensure that the encoding really was valid, right? And so that's sort of musing about looking back about how do we how did we encode things, and how do we check satisfiability? Well, in the case of the exponential size PCP, we used basically random combinations and this tensor test, right? These were the two parts that constructed the exponential size PCP. And in the case of polynomial size PCPs, we basically were able to push everything onto the multivariate sum check. Okay. But like, if you kind of take a step back, both PCPs are kind of fairly similar. Okay. They're kind of following the same approach. Okay. Of encoding a candidate satisfying assignment, having a way to test that it is close to that one. And if it is, then the second proof will help you check satisfiability. All right. Now we want to try to somehow reproduce this successful paradigm. So in a way that we will not have these blowups, right? Certainly, if we are aiming for linear size proofs, our blowup has to be constant. Certainly exponential doesn't fit and polynomial doesn't fit. And we discussed last time that anything that uses multivariate extensions is kind of stuck at n to the 1 plus epsilon. So we have to move to something else. So we need an encoding where we're going to have this property of so-called a constant rate. The ratio of the encoding to the message is constant. In other words, is that the block length is constant in the message size. And we also want to kind of to be in a good encoding scheme where sort of if you have two different messages that they differ at one position, then this difference is amplified to a constant fraction of the sort of locations of the corresponding encodings. Okay. But not only we want such an encoding, we want an encoding where we can carry out this recipe, right? And to carry out this recipe, we're going to need to have some proximity test to make sure that whatever encoding we have, we can test that it is valid to an encoding. Okay, it is not the case that every good code that you can think about has a good proximity test. All right. And also, even if we could test proximity, we would still need to test for satisfiability of the encoded message, right? So we need some replacement for the sum check protocol, for example, that will be compatible with encoding that we pick, all right? So it's actually a lot of structure that we need from this new encoding. And kind of, if you're familiar with kind of coding theory, if we just wanted this, like, well, any good code will satisfy, but satisfying these other properties is hard. And we actually, to this day, if we just look at the total number or total types of codes that are useful for constructing PCPs, is actually not that many, okay? Because they need all these extra properties. So the dual coding that we'll use is univariate logic extensions. And this is, you know, continuing this trend that polynomials are sort of you know, play an important role in arithmetizing and then testing computation. And so we're going to move towards univariate logic extensions. So where the encoding is going to be, the encoding of A is the univariate extension of A. So another way you can think about it is that the evaluation of this expression, this is the Lagrange interpolation of A on some domain, maybe F. And actually, it's not going to be all of F, it's going to be some subdomain L, okay? That's going to have size that is linear in the domain of the function we started with. We don't have to worry about the field being of linear size because, you know, fields have, like, you know, very kind of strict sizes. It's easier to think of a subdomain that we kind of measure the size of the subdomain as the thing we care about. Now, this encoding, you've seen it already in the lectures, the two lectures with Ton on the Fry protocol, and it's called the Reed-Solomon code. So we can define this code over a field F, domain L in degree D, to be all functions defined over L, such that when you interpolate them, they have degree at most D. Okay? And the relative distance of this code is 1 minus D over L, right? Because two polynomials of degree at most D can agree in at most D points, right? So the relative distance is 1 minus D over L. And if L is at least, like, say, some constant times the degree, then we can make sure this relative distance is constant, okay? So that is the code that we're going to pay attention to. And so there's some questions. Amit is asking, can I provide some intuition for why testing proximity is hard? Well, if you see it, if you see all the proximity tests we've seen, the BLR test for linearity, the arrest test for multivariate logic extensions, they all exploit, like, this magical structure of polynomials. And in general, an arbitrary code is like some combinatorial object that may not have nice structure, okay? For example, a code is testable. A necessary condition for that has to have low weight constraints in the dual code, and not all such codes have that. So you can actually construct codes that are not proximity testable, okay? But, you know, this only makes sense if you've seen some other codes beyond polynomials, for example, ones based on expanders, or even the good code, the canonical construction of a good code using concatenation. That one is just not at all clear, has any structure that allows for proximity. There's another question about, you know, A is originally, yes, you can think about it from N to F, and then we just identify N with, like, some domain of size, some domain H of size N, and we just identify it, okay? And we take, and then we take the extension not over all of F, but specifically on a sort of something L. You can think of L as something like 10 times H, okay? So that it will give you some decent relative distance, but we don't need to go for the whole field because maybe the field is much larger, okay? We didn't really pay much attention. We could have done this, by the way, for multivariate logic extensions and develop all of our machinery for going from a mini subcube to a medium subcube rather than the whole subcube of the whole field. It's just in that regime, we were not paying so much attention to getting the absolute best proof length. So it wasn't worth it, okay? Now that we're paying attention to proof length, now we want to have fine-grained control over these, you know, where are we extending to, like from H to L, and not specifically F, okay? So we're going to want to have that degree of freedom. And indeed, if you go back to the lectures you've seen on Fry, the test relies on reducing low-degree testing a function over f from L to L squared to L, to the fourth, L to the 8. We're using that degree of freedom to design the test. We did not change the field, we're changing the domain, right? So we will be using that degree of freedom. Now, today we're going to assume that we have a proximity test for univariate extensions. In fact, I guess I didn't update this, but we assume we have it because that's the Fry protocol. And we know we can do it, right, in a logarithmic number of rounds and logarithmic number of queries to test proximity to the Reed-Solomon code. The goal of today is to somehow bridge that last gap. Once we know we can test proximity to the Reed-Solomon code, how do we actually use it to check computations such as R1CS satisfiability? Okay, so that is, let's say, the arithmetization plus probabilistic checking minus the proximity testing, which will be given that we've seen it already. There's a question about, does cryptography give us better proximity tests than through information theoretic routes? I think that's a great question. I don't know the answer to that. I'm not sure if people have studied sort of, let's say, computational proximity testing. And so that's the plan, right? So we're gonna bet on making good use of the Reed-Solomon code. We know we can test it. Our goal is to somehow build an IOP of linear size, given that we have already tested for the Solomon code. Okay, and kind of what we think is good about the Solomon code is that, again, it has constant rate, constant relative distance. We already solved this part that we can test it. We're kind of trying to figure out whether we can do this. That's like today. Okay. Any questions before we continue? This was kind of setup and motivation so that we all know kind of where we're going. Are there other codes? Emanuele is asking, are there other codes besides Reed-Solomon or Reed-Muller for which we can test proximity? Yeah, so in general, well, we have, of course, the Hadamard code, which we already mentioned. We have, in general, any tensor code can be tested for proximity. For example, Reed-Muller is an example of a tensor code where you can consider any tensor of any arbitrary code. And that's kind of it, okay? There's a couple of other examples, but there's not many others. Of course, you can then bring, so Nishant is asking about, are these called locally testable codes? Yes and no, because our notion of proximity testing is slightly more relaxed than locally testable codes because we have the ability of asking help to the prover. So for example, the Reed-Solomon code is not a locally testable code, yet it is testable with the help of a prover, right? That's the Fry protocol. And because we're already receiving help from the prover for other tasks, it is okay to receive help from the prover also for testing, okay? So it suffices basically to construct an IOP of proximity, which is a much weaker requirement than local testability. Okay. Of course, once you construct general IOPs of proximity for arbitrary languages, then you can show that any code is testable just through some very roundabout reduction. But in terms of direct constructions, we don't have many codes. Okay, it's like Reed-Solomon. Tensors, a couple of other things is they need to have some structure we can exploit. Any additional questions? Yeah, I'll remark further on Nishant's question. It is crucial that we don't require local testability, right? Because that is pretty difficult thing to satisfy for a code. It suffices to be locally testable with the help of a prover. That is much weaker consideration, and that's fine, right? So that gives us a much bigger design space. Any further questions?
So I have a question.
Yeah.
Yeah. So So basically, when we ask the prover for help for doing proximity tests, somehow we are offloading some of the computation for locally testable onto the prover. Is that correct? So
It's
that is
not,
why
it's not quite about computation, it's about testability. So it's not about efficiency. You could ask these questions even with an inefficient verifier. And it's all about how many queries you make to the original input. Okay, so like these questions remain completely meaningful, even if the verifier is inefficient. So it's not about computation, it's about testability.
Oh, so is there not a requirement of locally testable codes to be efficiently locally testable?
It is made as a requirement usually, but even if you relax it, it will not make the problem any easier, okay? Constructing locally testable codes, even with an inefficient verifier, is just as hard because the issue is not so much is the verifier doing efficient computation or not, rather it is about how many queries you need to make to the candidate code word.
Okay.
Like the whole, like for example, if you pick up the property testing book by Oded Goldreich that covers big chunk of the property testing literature, the emphasis is really not on is the tester efficient, rather it is on how many queries are you making and what's the relationship between that and the distance you can prove. Okay, so now most tests that people are going to design will be efficient verifiers, and most kind of interactive tests you're going to consider are going to ask the prover to make efficient computations. But it is distinct from other questions such as satisfiability that become completely uninteresting if the verifier is inefficient. Testing is a type of question that remains completely meaningful even if all parties involved are inefficient.
So can't the verifier just read all the bits of the code word if it is inefficient?
That is not what I said. So we're limiting the queries, not the computation, right? So if we're saying the verifier cannot read more than a certain number of queries of the input, then even if it makes inefficient computations, the problem remains difficult. Okay, so it's an information theoretic statement about how many queries you make to the object being tested, not about the computation. It could be that it's solving, I don't know, next problems to decide which queries to make, right? That's fine. You're just paying attention to how many queries you're making to the input.
Okay, thanks.
So there's a question about, what is the connection between self-correction and proximity testing? They are complementary tools, right? So proximity testing is, are you far or not, right? Self-correction is saying, if you're close, then here's how to correct a location in the code word, right? Or of the message. So they are used often together, and many codes that satisfy one have a likelihood of satisfying the other, but they're like distinct things, right? Proximity is distinguished between far and close. Self-correction is saying, if you're close, then there is a way to kind of correct a location. Okay, great. Is locally decodable the same as self-correction? Almost. So you have these two notions that are, self-correction is not a precise notion, let's say. The precise notions is locally decodable code and locally correctable code. Locally decodable means that you can correct any location of the message, and locally correctable means you can correct any location of the code word. Okay, and these are like sort of standard definitions inside coding theory. You can probably find them in sort of any coding theory book. Self-correction is more of like an informal term that is used for codes that typically anyway satisfy both notions. All right. Today we'll not be using anything about self-correction or local decodability. It will all be about proximity. I mean, given that we're close, what can we do? Great. So anyways, I hope it's clear by now that somehow in understanding probabilistic proofs, it is helpful to have, let's say, a healthy amount of intuition about codes, because they play like a very important role there, right? So we're going to start out talking about a univariate sum check. Why? Because, well, we have this tool that we keep applying, multivariate sum check, that seems to be very useful in designing proof systems. Now we just decided that we're going to toss out multivariate polynomials and start using univariate polynomials. So it seems like it's a reasonable thing to do to try to reconstruct a subroutine for a simple task, which is just adding up a bunch of things, all right? Just about univariate polynomials rather than multivariate ones, okay? And then after that, we'll try to make good use of it. So here's the problem that we want to try to solve, okay? Not about satisfiability, this is going to be about summing things. So you give me a verifier that has oracle access to a function. The function for now, it is promised to have small degree, okay? Now, how do we know it? Well, we'll test it with the Frye protocol. And we're given, some field to specify the where we're working with, the evaluation domain for the function, the degree. And then we're given some summation domain and a claimed sum. So we want to check that the univariate function f on h equals gamma. Now, there is this hat here that I want to explain, okay? So, okay, I guess I haven't explained it, but the summation domain h and the evaluation domain L may be distinct, okay? Now, in the case when f was defined over all of f, capital F, or the whole field, we didn't have to interpolate because it was anyways defined everywhere. But here, just in case h is not contained in L, we may have to interpolate it and then evaluate, okay? So in order to make this sum well-defined, without assuming that h is a subset of L, which may not always be, okay? We have to say, okay, we want to check the claim where you interpolate f. Now it's defined as a polynomial over the whole field, and we evaluate it over h and sum it up, okay? All right, so now we're gonna kind of look at a couple of naive attempts to solve this problem, just to understand, what's hard about it, okay? One idea could be to just say, okay, look, take f, query it at every a, get back the values, and add up the answers yourself, right? So one answer is that, what if these sets actually do not share any points? Querying f at every location won't necessarily give you any values on h, right? So it means that we're going to have to interpolate it, okay? And we actually would need to query a at every value at d+1 values. So we can reconstruct f hat and then evaluate f hat over h, right? So this approach would require us to query f at d+1 locations. And even if h is a subset of L, and then you could say, well, I'll just query on h things, we're thinking of h as linear in the input size, okay? Because f will be encoding some assignment. So, and we'll be like sort of checking things over some linear size domain. So again, we're back to too many queries. All I'm saying is that if you try to solve the problem directly, of course, you're gonna have many queries. And even if h were small, if f is corrupted at a small number of locations, we would need to use self-corrections, which at this moment we did not discuss for its own code. So we need some protocol, okay? We can't just like query the function and go home. Another idea would be to say, well, we have a sum check protocol for multivariate polynomials. What if we just apply it for the univariate polynomial at hand? Right, so you just go back to the multivariate sum check. It is well defined when n equals 1. Just run it. Well, the first and only message is going to be the d+1 coefficients of f hat, right? Because we're shaving off one variable at a time. There's no variable to shave off. So the first partial sum is the polynomial that the prover is going to send. So the prover is just going to send us f hat in the clear. So here it is. And then we add up ourselves, we construct the polynomial claimed by the prover, and we check that it agrees with the original one at a random point, and we check the sum. But still, we are receiving an enormous message, okay? This is like tantamount to reading one huge symbol from the alphabet f to the d+1. It's like saying, prover, please tell me the polynomial in the object. I receive the object, I compute the answer, and then I check that the object I received agrees at a random point with the original object, but I still received a full object from the prover, right? So that's like cheating from the help of the prover, right? Even though we're reading one symbol, the symbol is enormous. It contains a whole object, right? So this is to say that solving the problem directly without thinking or applying the multivariate sum chain without thinking won't cut it. it will give us like linear amount of information we are reading from the prover. We want to do better. Okay. Some of these examples, either this example may be slightly confusing just because it's so trivial, but I still wanted to go through the trivial solutions before going to something like a bit smarter. Okay. Nonetheless, any questions about why these things fail? Okay, so if there's no question, let's go towards let's go towards constructing univariate sum check. So we need some new ideas. So we're going to solve the problem into two steps. First, we're going to make the problem simpler by reducing to the case where the degree of the function at hand is strictly smaller than the size of the summation domain. All right, because in general and in applications, it is going to be degree of interest is going to be maybe 2 times or 3 times the size of the summation domain. So we're going to first reduce the problem to a simpler case, okay, where the degree is bounded by the size of the summation domain. So this introduces a polynomial that you actually have implicitly already worked with in one of the worksheets. These things are called vanishing polynomials. Like given a set H, its vanishing polynomial is the product of x minus a for a in H. Okay, so it is the monic polynomial whose roots are the elements of the set. All right, that's what it means to consider the vanishing polynomial of a set. Let VH be that. And notice that if we divide out f hat by the vanishing polynomial of H, we're going to obtain 2 polynomials, the quotient and the remainder, where the remainder has degree that satisfies the condition that we want, and the quotient has the corresponding degree. And crucially, the sum of the original polynomial and the sum of the remainder agree over H, because the quotient is multiplied by the vanishing polynomial, and anytime you evaluate the vanishing polynomial over H, it goes away, it vanishes, right? So if you take the polynomial and divide it by the vanishing polynomial, you get a remainder that has the same sum as the original polynomial. Okay? So we're just using univariate polynomial division. All right? Great. Next step, we're going to be in this case and solve the problem by assuming some structure on H. We're going to assume that H has some nice structure and use algebra to basically say that when we are in this case, we can actually have an understanding of what the sum is. You might say, well, that's cheating. Like, why are we assuming that H has some structure? Well, we already did that. Like the multivariate sum check doesn't work for arbitrary multivariate domains. It specifically works for product domains, right? So the multivariate sum check doesn't work for any subset of f to the n. It specifically works for something that looks like h to the n, or maybe like h1 times h2 times h3, just something that is product form, okay? So already in the multivariate case, we leverage some like really special structure. We will do the same here. In the univariate case, we will not, in general, be able to solve it for arbitrary h's, but for special h's. What are the special h's? We'll assume that H is a subgroup of the multiplicative subgroup of the field, okay? Essentially, we're saying that H is cyclic, okay? So there is some way to describe H as like some omega squared, omega cubed, all the way up going around the cycle, right? So what we're going to prove, it's a very simple lemma, that if H is a subgroup of F star, then the sum of the remainder always is H times the constant term of the polynomial, okay, also known as G0. All right, that's it. Like always, like if you have a polynomial G hat of degree less than H and H is a subgroup, then the summation is precisely H times the constant term, the end. This is what it is. This looks magical, but actually it's a pretty simple, 2-line proof. First, consider what happens to a monomial. After all, a polynomial is just a linear combination of monomials. So let's first what happens for a monomial. Sum of a in H of a to the I. So this is like the ith monomial. Now, a because it's in the cyclic subgroup, can be written as omega to the j for some j, right? So now we have sum of omega j to the I. I swap the indices, and basically now we have a sum of all the powers of this particular power of the generator of the group. And we know that if you sum up these things, you're going to get 0 if I is not 0 modulo h. Otherwise, you get h if I is 0 modulo h. And the way you want to think about this is there's very good intuition from the complex, from roots of unity in the complex plane. Like, for example, if you sum up all the roots of unity in the complex plane, then you get 0, right? They have this sort of a relationship. So if here, if I is not 0 mod h, it's going to be something. And when you exponentiate it to the j, essentially you have a term that is summing up all the roots of unity. Okay? So it's going to be some picture like this, where these are all vectors that are equibalanced and equidistant, and they add up to 0. Okay? And whenever I is 0 modulo h, then you're just adding up a bunch of ones. How many? H of them. All right? So that's just like a basic fact of like roots of unity. And then when you take a linear combination of roots of unity, which is kind of all the monomials, we're going to get that because the degree of g hat is less than h, the only I that is 0 modulo h is the one for g0, and all the others disappear, right? So every other monomial that is positive power and less than h just balances out completely and disappears. And the only thing you're left with is the constant term times h, right? Great. This is like some kind of sleight of hand with roots of unity. And what we have learned is that in this step 2, the sum of a polynomial of degree strictly less than h is gamma, if and only if h times its constant term is gamma. That's what we've learned in step 2. Okay. So we are about to assemble these 2 steps into a protocol for a univariate sum check. But before I do that, are there questions either about step one or about step 2? Step 1 is just basically reducing the degree without changing the sum. And step 2 is basically saying if the degree is less than h, then we can control it or understand it through the constant term of that polynomial, because h has structure. Okay. By the way, just for your interest, for those of you that like finite fields and like I guess cute math symmetries, there's a similar statement that holds if H is an additive subgroup of a field. So think about maybe a vector space in f to the n, right? And what is going to matter is actually the highest coefficient, not the lowest coefficient, the highest coefficient. And yeah, there's like the proof is actually much less obvious. One way to prove it is using kind of directional derivatives, and it's a very beautiful and sort of non-trivial statement. I mean, not non-trivial, but not obvious statement about the case of additive subgroups. But either way, basically, some subgroup structure, whether multiplicative or additive, helps you understand the sum. Okay. And so there's a question there, what is F star? Yes, F star is the multiplicative subgroup of the field. So it means that you take the field, you kind of throw out 0, and you only consider the multiplication operation rather than the addition operation as well. That gives you a group. And not only it's a group, but every multiplicative subgroup of a group is cyclic. So we know that H is generated by some omega. These are very kind of useful kind of facts about finite fields. Further questions? Great. So now let's assemble these 2 facts into a protocol. So let's say that you have the prover and the verifier. what the prover is going to do, it is going to compute the quotient and the remainder, which here, for reasons I don't understand, became from G to P, but okay, fine. No, now I understand, because there's a claimed gamma, right? And so what you want to prove is that the remainder has a specific constant term, right? So you're going to pull out from that remainder all the non-zero powers, okay? And then put in yourself the constant term, and you're going to send H and P to the verifier. The verifier is going to test that H has degree that is close to what it should be for the quotient, and P checks that it is close to degree that is -1 what it should have been for G hat, right? Because P hat is supposed to be like all the non-zero kind of coefficients of G. And then we're just going to test at a random point that this equation holds, right? F of S equals H of S times VH of S plus this thing. So that means that I query each of these at one point, and then I evaluate this expression. So we're going to argue this carefully. So suppose that F hat evaluates to gamma, then the verifier excites with probability 1. Why? Well, okay, I guess I should explain that. Don't have a why. Because we know that if that is the case, then G hat at 0 times H is going to be gamma. But what does that mean? It means that if we pull out the constant term, it is going to look like gamma over H. And then we don't care what the rest is, right? So we just ask the prover to give us what the rest should have been, and we just check that things have the right form. Okay? So if F passes this polynomial identity test, it means that F looks like something like H times V plus X times P plus this thing, which means that whatever this is, it is a polynomial of degree less than H, whose constant coefficient is gamma over H. So when you multiply it by gamma, you get gamma. But by H, you get gamma, right? So because we're talking about specific coefficient, we just had to like kind of force it in ourselves in there, right? And of course, this X in front is just to shift that polynomial up and force it to have no constant terms that could interact with this one. So let's look at the soundness analysis. Suppose that F hat does not sum up to gamma, then there are two cases. Either whatever the prover sent, either of them is far from the respective low degree sets of degree D minus H or H minus 1. Well, in this case, okay, or they're both close to some unique polynomials H hat and P hat. In the first case, we rely on the low degree test that it will accept with small probability because one of them is far, right? Like it would be like running Fry protocol on the correct degree on H and P. In the other case, it must be that this polynomial identity does not hold, because if it did hold, it would tell us that F hat would sum to gamma. So it cannot be this polynomial identity holds. But look, we are testing it precisely here. So the identity test will accept with utmost probability here is D over L plus the error term of making one query into a delta noisy variant of H and a delta noisy variant of P, right? So we pay a 2 delta here, okay? Because, you know, maybe the prover doesn't tell us the exact polynomial, but because we tested it, we know that they're close to the right polynomial, right? So this is the error that comes from testing this identity, and this is the error that comes from the noise left over from being close to the corresponding low degree set. There's a question, and we take L to be order of D. Yes, so we take L to be order of D. And so now we go back and we see that the amount of information that we've received is like linear in D, right? Well, there's a question about how do I get the D over L term, because we are comparing a polynomial of degree D with another polynomial of degree D right? And we're testing it at a random point, so it's d over L by the sort of Schwarzschild lambda, right? We're sampling a random S in L, and there's at most d places where these two different polynomials can agree, right? So we'll pay an error that is d over L in the worst case. Maybe some of those roots are outside of L, somewhere L in F, and then in reality it would be less, but maybe all the roots are in L. What do I know, right? So that's where d over L comes from. The plus 2 delta is because we're making one query to H and one query to P at a random point, okay? And they are noisy, delta noisy. And for now, you know, I'm kind of putting behind the rug, under the rug whether F is noisy or not. Let's ignore that for now. So this is a univariate sum check with linear size. We're sending information that is basically 3 times the size. Like if F has a certain size, we're sending kind of 2 more things of that same size as F, okay? To enable the univariate sum check to work. In fact, this is not even an IOP, by the way. This is like a PCP. So it looks quite different from the multivariate sum check, but it is similar in that it exploits whatever structure we can about kind of sets of a certain structure. So there's a question: can we do log test with log T queries? Log D queries? Yeah, that is the Fry protocol that we've seen. So when I write this thing, I mean use Fry. Okay, so each of these 2 tests is going to cost us log D queries. Okay, and of course further interactions. I guess when I said it's a PCP, I meant you know, without the retest. And then where does the reduction complexity comes from compared to trivial solution is because we are touching F only at a random point. We are not doing anything else with F ourselves. And then we are making log D queries, 2 queries here and log D in the loaded test. And overall, we are making log D, which is exponentially better than order of D queries of the trivial solutions. Hopefully that, yeah, so it's an exponential improvement in a number of queries to the corresponding, I mean, to all whatever objects are sent in the protocol. Great, good questions. So look, the algebra in the previous slide was a little bit fast. I didn't linger over too much because all the details are there. You can check it offline. I really would like to get, I mean, I wanted to spend a little bit more time on the protocol itself and the protocol that builds on top of that. But the algebra is like truly like, you know, sort of, there's nothing too magical going on. It's just roots of unity and then polynomial division. That's it, okay? Further questions before we, because this is the last slide on the univariate sum check. Once we have it, we want to go up to our 1CS. That's the next thing we want to do. Leverage it to check satisfiability of rank 1 constraint systems.
Sorry, the same question, but about now the second part of the test. How, like, so yeah, we use Fry to test low degree in log D queries, but how do we check it at a random point with log D queries?
We don't need to do self-correction because we're checking at a random point. So it's on an unbiased point. If you're delta close, then there's delta probability that you will land in a noise and the rest are going to be fine. So this is an example where self-correction is not required because our query to the polynomials underlying the noise are completely random. So if we know that, let's take H, okay? If we know that H is 10% close to some polynomial H hat, it means that 90% of the time when we query it, we will get the answer from H hat, the end. Now, 10% of the time, we'll get some garbage, right? But we just absorb it into this term here.
So H and F, they are sent to us. So for Fry, we need to send, we need to repackage them, right? And send, wait, so they are not send us coefficients, they are send us evaluations. That's right.
Yes, they're sent as evaluations. Yes.
They're sent as evaluations. That's why we can check. Yeah, thank you.
Yeah. So the polynomial, has the coefficients to perform the polynomial division. They're coming out from the symbolic division, right? But after it does that, it evaluates them over L and sends them in this format, right? So that it can be logically tested, and also so that we can do this polynomial identity test. Good question. Yeah, I did not. Maybe I really should make a note to make that a bit more explicit. That the prover is sending the evaluation, not the coefficients.
Maybe last question. So to make sure I understand, at a high level, you're reducing the claim about the sum being equal to gamma to a claim that there exists two polynomials H and P that satisfy something.
Exactly. So we are translating a summation question to some polynomial identity test between the original polynomial and some other polynomials the prover can find and send to us. So then it's pretty simple what to do. Just whatever additional polynomials, claimed polynomials that show up at the doorstep, test them for low degrees, for the corresponding degrees. And then once you do that, just run the polynomial identity test on the equation that they were supposed to satisfy. And that's it, right? So we're just converting some sum check problem to an identity test on some magical kind of formula. Okay. Yeah, that's a good way to summarize it.
Maybe another quick question. So, I mean, if my understanding is correct, the term 2 delta comes from the fact that when we test separately H and P, the arrows might be in different position, right?
Yes, and a slightly more accurate analysis, you can actually make the two go away.
Yeah, that's what I was thinking. Like if we test like both H and P at the same time, maybe taking a random linear combination, shifting the degrees, maybe we can like remove the two. But okay.
Yeah. No, this can be done, but that's that's like it's more advanced, right? It requires sort of understanding statements such as random linear combinations, and then testing implies that the errors are going to be correlated in locations after the test, right? And but yeah, these things are used in practice, and if you test H and P with shifts together in the same with the same randomness, you can get to go away. Yeah, but these are like the intuition is strong. The analysis has to be there because it really the fact that it works is not entirely straightforward, right? So. Great, good point. Okay, so let's continue to the protocol itself. So now we're gonna look at another stepping stone, okay? Where rather than looking at a sum, we're going to look at a general problem of checking whether two polynomials are related by a linear transformation. So you give me f and g over L, and then I'm asking, okay, take the corresponding polynomial, f hat and g hat, evaluate them on H. You're gonna get two H-size vectors, and convince me that these two vectors are related by the linear transformation M, like some matrix. Okay. Now it's clear where we're trying to go, right? Like we will eventually have to deal with R1CS, and there are matrix vector multiplications we want to check, right? So here we're just trying to figure out in isolation how to do that. Okay. So that once we learn how to do it, we can assemble it into like the R1CS protocol. So our task is to check this type of problem, and our approach will be to just reduce it to a sum check problem via one round of interaction. Okay. So yeah, so that's what I said. We're going to reduce to the invariant sum check claim. So notice that this claim is nothing but a bunch of equations of this form, right? It says the 8th entry of G is this particular row of M times F, right? Of course. And we have like a bunch, like this matrix vector multiplication is a bunch of vector times that, it's a bunch of inner products. So here they are. I can also rewrite this as a summation, right? And say, look, let's move this on the other side, consider these to be coefficients of some univariate polynomial, and ask whether this univariate polynomial is identically zero or not, right? So it is identically zero if and only if all these equations are held. So I'm kind of storing in the coefficients of a polynomial all the things I want to check. All right? Great. And of course, what do I mean by integer of A? It's just there's some bijection between kind of field elements in A and the integers 0 through h minus 1. Now, for any r do I mean h? I probably meant something else. Probably meant f here. Let's make a note. For any r in f, let me make a note. The valuation of this polynomial at r can be written as follows. I pull out this r again with that one as a sum, and this part here is over here, right? Because I can just move it inside and reindex. Okay. And equivalently, I can just apply the linear transformation to the powers of r rather than to f. Okay, so that I can index the same way g and f. Okay. So I'm just going to call r m to be the vector that corresponds to the linear transformation m applied to r. And then I logically extend the powers of r and the linear combination of the powers of r into their own polynomials, r hat and rm hat. Great, but actually now we have a univariate sum check problem where the addend has degree that is d plus h minus 1, right? Because these guys had degree d, and then each of these extensions have degree h minus 1, less than h, right? So what I've done is I've taken this problem and I've rewritten it as a sum check problem for any choice of r. So now intuitively, of course, with a random choice of r, this condition will be equivalent to this condition with high probability. But let's see it in action. How would we do it? We would ask the verifier to send a random element in the field, and we're just going to run a sum check protocol for this expression for the r chosen by the verifier. And then whenever the sum check protocol asks me, please evaluate the addend at a random point, I am going to query f and g at s for that. And then I'm going to, as a verifier, evaluate myself the expression r hat at s and rm hat at s, okay, to give back the answer. And this can be done in a linear number of operations. Right now, we are not going to go for a sort of a saving computation. We're just going to sort of check satisfiability with a small number of queries, not a small amount of time. And the sumness adder is roughly, not roughly, it is exactly the degree of this polynomial, because we're evaluating at a random point, and degree is h minus 1 over f, right? Plus whatever is the error of the sum check protocol underneath, which we already kind of argued in the previous slide, right? So that's it really, right? We can just massage a linear transformation into a univariate polynomial by basically by viewing it, the linear transformation as two sums, and then reindexing so that we can sort of absorb the linear transformation inside the randomness. And we can compute the linear transformation ourselves, not on f, but on r, right? It's like the association of multiplication, right? If I have multiplying three things, I can first multiply 1 and 2 and then 3, or 1 multiplied with 2 and 3, right? So here I've introduced this third object, the random one, and I can first multiply the randomness, which I know, I don't need to query anybody for that, with m, and literally extend after that. Any questions about how to check linear equations?
Yeah, maybe you explained this and I missed it. Why do you change the order of the indices in M?
Because I would like to, it's a good question. I probably didn't explain it very well. So we want to write one summation over A, over like 1A, all right? Here, if you see here, G and F hat are indexed by two different summations. And right now, in some sense, I'm thinking over H squared, right? It's too large H squared. I really want to think just over H. So I need to change this indexing to be also with A, right? One way to do it is to basically absorb the linear combination into R first and then multiply with that, okay? It's like saying when, one way to think about it is that when B equals, so pick a particular A0, right? When B equals that A0, I'm going to gather together all the contributions to that A0 and put them all in one place, which is exactly this one, right? And now they're like over the same domain, indexed in the same way, just the annoying part of rescrambling through linear combinations is happening in its coefficient, right? So it's just like moving the sum from over F to like kind of over X or over R, right? But overall, I'm still computing the same sum. All right. I hope this clarified a bit. Good question.
So basically, this version of sum check cannot be iterated. We cannot have iterated sum over H1, H2, H3, each of them being a group, right?
Sum over H1, H2, H3, that becomes a multivariate sum check. No?
Right. Wait, right.
So look, these techniques can potentially be used orthogonally with one another, where, you know, if you're running a multivariate sum check over H to the n, and H itself is too large, then you can run a sub protocol for the univariate polynomial that is sent for that round, and, you know, have a sub protocol to prove that sum if you don't want to do it directly, right? But when you start considering like products, you know, that you're moving to multiple variables, right? Right, good question. Further questions? Again, like there's not a whole lot happening here. We're just kind of, we have one tool, the sum check, and we just have this task, and we just have to somehow, one way or the other, reduce to it. And that's it. We just use randomness to help us with that. Okay. Right. Maybe another way to view it, maybe it's like just a quick summary. We had we have an expression that looks like, no, maybe not A, let me use something else. G equals M times F. Forget the hats for a moment. I'm taking an inner product basically with something random, right? And because these things are bilinear, I can like flip it over on the other side, and there's like, you know, M transpose, right? F. And that gives me further something that looks like RG minus RM transpose F, right? But that's just a sum over some index A of this expression, right? This is already a polynomial, this is already a polynomial. I can just logically extend myself this one, logically extend myself that one, right? So that's all that's happening, okay? We're taking a random linear combination. Why? Because a random linear combination will create a sum. And then a sum we know how to solve. I liked using this, you know, much more explicit kind of notation to really see what's happening. This one is a little bit more kind of compressed about what's happening, but, you know, maybe some people will find it helpful in that way as well. All right, let's move on to the protocol. Now that we have how to check linear equations, we go back to constructing things for our 1CS. So this is going to be a protocol where we are given the three matrices of our 1CS and the public input, the candidate witness for the prover, and of course the verifier just receives the instance alone. The protocol will work as follows. First, the prover will construct the full assignment from the public and sort of private part. And first, it will kind of compute this, let's say, shifted witness that will help us deal with the public input, right? So the public input that is known to both parties, we're going to compute to this shifted witness. And we're going to send over this part, like this witness shifted by like the public input to the verifier. And also we're going to send to the verifier all the linear combinations of the full assignment. So AZ, BZ, and CZ hat evaluated at L. Why are we sending these? Because these are going to be the ingredients for the sub-protocol for linear combinations. Now, to prove that AZ, BZ, and CZ are, that AZ times BZ equals CZ, we're going to use a trick that we have already seen in the construction of a linear PCP for R1CS, which is to divide by VH and obtain the quotient polynomial. Okay? So we're going to send all these things. Notice that F for the full assignment is defined by assembling FW with U hat, right? So I don't want to just check that the R1CS is satisfied. I want to send it's satisfied with a certain prefix. So the way we're doing it here is that the prover is sending us part of the assignment, and we, as a verifier, complete it to the full assignment. So this property is precisely why we defined FW this way. Okay, great. So now we're going to sample S and L at random. And first, we're going to check that the condition on FA, FB, and FC for this entry-wise product holds. All right. So this is assuming that FA is encoding A times Z, assuming that FB encodes B times Z, assuming that FC encodes C times Z. We check that AZ times BZ equals CZ. That's what this is checking. And again, we have used this trick before in the worksheet for our R1CS linear PCPs. All right. But now we need to check that the linear combinations are as claimed. So we send the randomness as in the previous protocol. And for each matrix in ABC, the prover is going to compute the kind of polynomials of the sum-check protocol necessary to argue that this expression, which was the sort of randomness times alleged linear combination minus shifted, kind of linear combined randomness times the original vector, equals the quotient plus the remainder. And notice here, gamma over H doesn't appear because gamma is 0. Okay, we are asking that the sum is 0. Right? So the prover will send kind of all these polynomials to run all of these univariate sum checks. And so the verifier will check each of these at a random point, and it can even be the same point as the other ones. And then, of course, anything that is sent has to be tested against the degree. And these are the degrees that are used. And that's it. This is the protocol. So the prover is sending a linear amount of information here because this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 10, 11, right? 11 times the size of the problem as polynomials, so as evaluations of polynomials, plus a bunch of Fry protocols that each of them have linear communication anyways, right? Because it's a geometric thing. L plus L over 2 plus L over 4, blah, 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 right? So you halve the size of each polynomial. The communication complexity, the proof length in Fry is linear. And the query is overall logarithmic. And we're going to go through it a lot more carefully in the next slide. But let me just say that there is actually no need to run 3 sum checks. I'm writing it this way, but you can even combine them together into 1 sum check. There is no need to run a bunch of Fry protocols. You can combine them into 1 Fry protocol. These are things one does in practice. Here, I am not doing them because that's more things to understand. Okay. The whole point here is that it's, we're just assembling the components that we have developed in a pretty straightforward way to check their R1CS relation. Okay. Before we move to the next slide, where we go a little bit more carefully over the analyzing this protocol, are there any syntactical questions? We'll analyze it in the next slide, but any syntactical questions about what's going on here?
So we assume that L and H are disjoint set because we divide by this vanishing polynomial, and this we don't want to be 0.
Yeah, yeah, and this is the reason why at the beginning I was not assuming that that H is a subset of L. Yeah. Further questions? Now, hopefully the intuition of the protocol came across rather nicely in the sense that we built it up piece by piece. Had we started here, it would have been pretty complicated. But I tried to basically open it up fully, like But for the low degree test, this is all that's happening, right? So I like unrolled everything, including what the univariate sum check does, okay? And like, it's really not like these abstraction barriers or abstractions for univariate sum check and linear equations, they were there just for understanding intuition. Then you can even rip them away, and the whole protocol is pretty straightforward, okay? Like we are only assuming that we have the low degree test. Everything else is explicit here.
Can you explain again, how did the verifier embed the statement into the check?
Whenever I write f here, the verifier will have to query f at s, but f is not sent anywhere. It is some sort of virtual oracle that is assembled from an actual oracle sent by the prover and the statement obtained by that the verifier has at hand, okay? So it is assembled to have the structured by design, because I am kind of multiplying whatever the prover sent by some vanishing polynomial that forces this function to have the correct value over the part that corresponds to the input. Okay.
So he makes a low degree extension of the statement, but on what points? On
the rest, and then you evaluate it on L. So the prover interpolates this part and then shifts it, knowing that I will be multiplying by these things. Okay. So we kind of, by definition, we construct an oracle f that combines the part that we don't know with the part that we do know, so that the part that we do know, and must be the one that we have, has the right value in the right domain. Okay. Good question. I could have left it out of the slide, but I still wanted to put it in to show that there is a full protocol that is really not complicated. It's fully specified here, but for Fry, right? Great. So we have 10 minutes, and I think I need 5 minutes just for the next slide. And so let me go through it, because I think it's worth it. So I've kind of copied the protocol here, a little bit smaller. Of course, we're not going to go through completeness. That one is the easier side. Let's talk about soundness. Suppose that the instance that we're given is not satisfiable. It's not in a language. So first, kind of regardless of that anyways, if the prover sends any function that is delta far from the respective degree, then we're done, right? Because the Fry protocol will catch it with decent probability. So suppose that anything that is sent is delta close to some polynomial. So let's give names to all these polynomials. Basically, take the function, put a hat over it. That just means the closest polynomial that is delta close, right? Because the instance is not satisfiable, one of the following must be true. Either the Hadamard product condition is violated for the closest polynomials, or one of the linear conditions is violated. Okay, or okay, I guess I didn't have it here, or like kind of a where you go. Actually, never mind. This is the only reason, because f hat it's already sort of has u inside it, so I'm not counting u. So either one of the Hadamard product is violated, or one of the linear conditions is violated. Because if both of them, if the Hadamard product is not violated and none of the linear conditions is violated, then that by construction it means that this is in the language, right? So one of these must go wrong. All right. In case one, it means that if this Hadamard condition doesn't hold, it means that you cannot write this polynomial equation. Well, in that case, this test is going to accept with probability at most 2h minus 2 over L plus 4 delta. Why 4 delta? Because we are querying 4 things, 1, 2, 3, 4. And again, the 4 can be made to go away. It doesn't matter right now. And why 2h minus 2? Because we're multiplying 2 things of degree h minus 1. So that's 2h minus 2 over L, right? Great. In case 2, it means that except with probability h minus 1 over f over the choice of R, which is reducing the linear condition to univariate sum check, this equation cannot hold, because if it did, then it would sum to 0, right? And again, then we have this test running. In this case, the verifier would accept the probability at most 2h minus 2 plus for delta, because y to the 4, because it's 1, 2, 3, 4, right? And y to h minus 2, because again, we have two things that are being multiplied, and that's the highest degree in this polynomial identity. Okay? And so that's it. That's how you analyze soundness in this one. All right? It's rather straightforward. Okay? We are just kind of reducing everything we know to polynomial identities about low degree polynomials, and then we run the Fry protocol to make sure they are low degree, and we're testing these polynomial identities at random points. Someone is asking me to repeat case 2. There are two sources of error. There is the randomized reduction from the linear condition to the univariate sum check, and then is the error of the univariate sum check itself. This is the reduction over R, right? And this is the error of the univariate sum check, right? Because we're saying if the linear condition doesn't hold, then with high probability, we will get a false sum check statement, right? But there is some error there over R. It's this one, okay? Once you have, if you're lucky as a verifier, like most of the time you are, you reduce a false claim about linear combinations to a false claim about a sum, then now you incur the sum check error, right? And that sum check error is this one. Okay, I hope that clarifies it. Further questions about the analysis? So kind of taking a step back here, kind of what's happening is that our bet on univariate polynomials came to pass. We found the right structure, we created a univariate sum check, and then arithmetizing things and manipulating them to turn them into things we can understand was also rather simple. In some sense, you know, there's a little bit of magic in univariate sum check, sure, but once we could test proximity, then we were most of the way home, okay? One just had to like figure out the right way to arithmetize the computation and basically reduce your problem, possibly with interaction, to low-degree testing of univariate polynomials, right?
So I have a question regarding zero knowledge. It should be not too hard to get it even to perfect zero knowledge, right?
So we did not talk about zero knowledge here. Achieving zero knowledge requires some care. Like almost all zero knowledge surgeries, it is a delicate surgery. There are ways to add randomness here, you know, to mask some things, to make the whole thing zero knowledge. But you know, it's not something that we cover here. I'll just say it can be done. It is delicate, but it doesn't really change the protocol too much. It's like a small diff, but it's a very fragile diff on this protocol. Okay. And of course, the goal would be to protect, you know, this W here, which you can think about it as a private input of the prover, right? But intuitively, kind of, you would randomize all of these things, right? Then when you run the univariate sum check, you're going to have to do some more randomization here. So it requires sending some additional polynomial there too. Can be done, and you know, in the literature it is done. It has also been implemented, and yeah.
But can you turn this protocol into an argument of knowledge? That can I extract the witness?
It is already such. We basically proved knowledge already, because we said that not if the verifier accepts with high probability, it's not just this one is satisfied, it is specifically satisfied by whatever happens here. So like the thing that satisfies the statement is this oracle that the verifier, that the prover sent, possibly after, you know, removing noise. Okay. So basically, like, just we're not talking about knowledge in this, I mean, proof of knowledge in this course. I'll just say that for those of you that understand the difference between soundness and proof of knowledge, every proof of soundness I've ever seen about any PCP or IOP is already a knowledge proof, up to some, like, you know, minor like care, all right? And so is this one. So, okay, good question. So I think for me, this is a good time to stop and take further questions. So let me stop the recording.